All right, so good evening. It is 35 after. I think traditionally this is about when we start our meetings. So, hello all. Welcome to our December AF Mixer meeting. Thank you all for joining. It looks like we have a decent complement here tonight. All familiar faces all around. So, um, anyway, we've got a couple not presentations really, but topics that we're going to be discussing this evening. But before we get to that, we'll go over our usual preamble, which is to state that note that we are recording these meetings. All of our meetings are made available to the public for viewing on the SOAREX YouTube channel. And if you are here and participating, it is understood that you have accepted the recording and publishing of the video and recording. So with that, we will get going. We have regrets tonight. Both Ken and Michael are unavailable to join us this evening, so we will hopefully see them at the next meeting. But other than that, looks like I said, we've got a full screen here. So, are there any additional topics or discussions that anybody wants to bring to the front now, so I can put it on the agenda? If so, please come now. Okay, and that includes any info to share if you've got anything important or what have you. If not, we can talk about it during the round the screen session that we have after the topics are presented. So, all right. Well, with that, I think we will get into the meat and potatoes of the meeting tonight. So, flip a coin here. I'm just going anti-alphabetically here with Dave. If you're ready to talk about your high-powered rockets, are you ready to go? Okay. All right. Well, let's get the show on the road then.
Got to share my screen. Got to figure out which screen to share.
It's okay. There you go. I see it.
There. Can you guys see that?
Looks good.
Okay. What I'm going to talk about today is basically how I go about building a rocket. It's not going to be a detailed discussion. It's going to be more showing you pictures of the process I go through each stage as I built the rocket. Because one of the last rockets I built, I actually photographed each stage, and I thought I'd just talk a little bit about it. So basically what I'm going to do, I have one slide on just how a rocket works, one slide on rocket design, and then the rest are just pictures. I'm not going to go into too much detail about rockets. Again, it's just a photo essay of the build process. And so what I'm going to be talking about, the build process of a scratch-built rocket, a rocket completely from parts. So it's not a kit. You can go buy kits, and they're usually anywhere from $100 to upwards of $600-$700. You can get a rocket, and you go and it comes with instructions and you build it. But most of the rockets I built, just like the electronics I build everything from scratch. So basically, how does a rocket work? Because this is kind of important when I build a rocket. It's you got to know how things works. So basically, if you can look at this picture here, a rocket has a center of gravity, and that point is a point at which the rocket will tumble. It rotates around that point. So as it's traveling, it's going to always move around that center of gravity. And so if you look at the forces of rocket in flight, you've got the center of gravity, right, which is shown by the weight vector coming down. So that's the weight of rocket. Then you've got this thing called lift. And what lift is coming from is from the fins. And the lift is what steers the rocket around that point. So basically, if you look at a wind vane, the center of gravity is the point that's fixed here, and you've got this big fin at the back. And so as the wind blows across this, the fin always aligns in the wind, because if it didn't, it's going to kind of get blown back. And that's the same thing happens with a rocket. It's basically weather vane. It's a weather vane, and the fins are the weather vane part of it. And that's basically it. There's no math, no fancy equations, just very, very simple from a high level. Now, the next part is rocket design. So, this is very important as you're building a rocket, unless, as I said, you're building a kit, which it comes pre-established what all the points are. So the key thing is that you have to do some calculations to figure out how the rocket's going to fly. And typically there's a set of equations called Barrowman's equations. And way back when, that's how people used to design rockets. They'd use Barrowman's equation to try and figure out whether the rocket was going to be stable or not. That is, there was enough distance between if we go back, there was enough distance between the center of gravity and the fin area. If that area is too small, it won't weather vane into the wind very much. If it's really far back, it'll weather vane too much into the wind. So there's a sweet spot. And so that's what Barrowman's equation does. I used to use that way back, in the day, but now there's rocket simulation software, just like LT Spice. There's Roxim or Open Rocket. Those are probably the two most popular software types of software available. Roxim is purchased. I purchased that. I did used to use that many years ago, but since then I've switched to Open Rocket, which is open source. It's free to use, and so most of my rockets now I design using open source. And here's the open source. Here's the Open Rocket window. When you open it, you build a rocket in pieces, and basically what you need to do is set the number and size of the fins. Set the length of the rocket, because the length of the rocket is going to be important for how much space you've got for your parachute, how much space you've got for your payload bay, how much space you've got for your motor. Because if your motor fits in there, it's pretty big, you want to make sure you've got enough space in there. Also, the size of the parachute. So when the rocket's coming down, you have to have a certain size parachute to make sure it hits the ground at a reasonable rate that where it won't get damaged. So in Open Rocket, you go in and you set all the parts, and all the parts, you can see all my parts list here, and they all have weights associated with it. So based on this, it calculates the overall mass, and you can see it here, mass with no motors, 48 ounces. I don't know why this is in ounces. I normally have it in grams, and then it's showing inches, which I don't use inches. I typically use meters. I use the metric system. So, and that's giving me the information based on the parts I selected here. Now, one of the things I have to do, and you'll see this later on, is once the rocket's built, I override all these things, because these parts, they're not going to be exactly what the parts you use. They may not be the exact weight. You have to, you're using epoxy, glue, using all kinds of different pieces, bits and pieces, which adds weight to the rocket. So enough said about the theory. Let's get into some pictures. So when you're building a rocket, the first thing you have to build is you have to build something called a motor mount. And so basically you've got a set of centering rings. So these rings go inside the tube of the rocket, the outer tube of the rocket. And you have basically, you could have 2, 3. I've built some with 2 or 3. And basically what these centering rings do, they center the motor. So it's center going up the tube, the rocket tube. So the force is centered in the middle of the tube, of the body tube. So in this case here, so you could see I glued the first, I start off by gluing the first centering ring at the bottom. And then I've got the motor mount tube. Then I would put the second centering ring at the top, and I'd use a fin, just because I glue my fins inside to give extra strength, just to make sure I glue this at the proper height above the bottom centering ring. And this is a jig I 3D printed to help me make sure my fins are perfectly aligned and straight. So let me just stop this. So that prior, these centering rings I bought. I bought these. You could see they were laser cut. You could see the laser scoring the burn marks from when it burnt. So this I bought from a store. I didn't build my own, but in a subsequent rocket, I did build my own, and I figured out how to use my milling machine to actually go and create rings. Now these are for bulkhead rings. They're not for centering rings. They're for payload bay. But I just brought this in to show you, that my CNC machine is actually cutting the rings out. And in this rocket, the second rocket I built, I actually cut the centering rings out using my CNC machine. So here's a CNC machine here. It's cutting out the fins. You just saw the fin I was using, so that I placed between the 2 centering rings. So here you can see it's milling out those fins here. So once you got all your fins, milled out, and you got your centering rings set up, you do a trial fit just to make sure everything fits okay. Then you go ahead and you glue it. And you can see here in this picture, I've got epoxy. You see I'm gluing it both at the bottom centering ring here and along the sides of the motor mount tube. The reason why you need to do all this gluing is because, keep in mind, the motor mount is the force from the motor is directly transferred to the motor mount tube. Then this motor mount assembly needs to transfer that force from the motor to the tube. Otherwise, this would go right up through the outer tube. So you have to do a good job of epoxying this. And so I do my fins this way. It's called through hole. You're doing right through or through wall, through the outer wall of the tube. And I epoxy everything together. Now this little nut here, it's not over here. Before I start gluing, you have to drill these out and put these nuts in, because they're for these little screws here, and they hold the motor in place as the rocket's flying. And here you could see it's a closer look of it's glued together. There's that little nut. And here you could see now, after it's glued together, that's the motor inside the motor mount tube, and you can see the bolts here. So basically what happens is I take a piece of like plywood or light plywood, or maybe even a small light piece of metal to go across here, and that holds this motor from shooting back. The motor has a little lip and goes against here, and so the motor, as it's firing, it's not going to go through the motor mount tube. It's going to transfer the force to this tube, which then has to get transferred to the outer tube. So the next step, it's very important that you label which end is up to. Trust me, this I've gone and I've done things backwards, so you use lots of arrows to make sure you know which way is up. So the next step is you put your shock cord. And basically what that shock cord does, it's going to attach to this next stage of the rocket. So when the rocket opens, the rocket stays together. And basically you just drill some holes and you just put some epoxy in there, tie a knot, epoxy it so it can't physically get pulled out through the hole. And here's the outer tube, the body tubes. And so the next step is to actually mark them and score them. So as you slide them down, they fit over the fins. And here you could see the body tube where it's scored, it's coming down, and I've got it epoxied at the bottom, and I've also got it epoxied inside. So if you go back to this tube, this bulkhead, this centering ring, you're going to put epoxy around the edge of this. So as it slides in, it gets glued into the tube. Now I bring the shock cord out the butt end of the rocket because I don't want any glue. I don't want it to get accidentally glued to the centering ring or to the actual body if any glue drips. I want to keep this no glue. And you can see I got it clamped in place there. Then the next step is you put some fillets on there, and that it does two things. One, it helps to transition force to the body tube. Not only does the centering rings transfer the force to the body tube, but here you've got epoxy along the edge of the fin to the body tube, so that helps to transfer force as well too. And you can see here closer, and it looks pretty gross there, but there's a trick to clean that up later on. And here it is, completed. It's glued, and you see the rocket starting to take shape. There's the shock cord coming out, and here's a better picture showing the shock cord coming out. So another stage is going to fit in here. The payload bay goes in there, and another stage goes in. So the next step is what I do is I take just caulking, outdoor, grade caulking, and I just put some caulking, and I use my finger and I smooth it, and I get a nice smooth area here that's paintable, and it looks better when it gets painted. So next step is to build the payload bay. So here's a payload bay. So this tube fits inside of that other tube, the outer, the body tube, and then there's bulkheads. And you saw at the milling machine, I was cutting some bulkheads for another rocket I built. But here, in this case, I purchased these bulkheads, and they go at either end of the payload bay, and they fit inside the body tube. And you can see this eye bolt is where the shock cord gets attached to. And there'll be another eye bolt here, which goes at the top of the payload bay. And here you can see how it fits in. So this is flush, the wall here, and this outer, this center, this bulkhead is completely flush. So it fits right inside that tube. It slides right inside that tube. And here now you can see the rocket starting to take shape. There's a payload bay, fits inside this tube. And then this tube fits on top of that, this payload bay. And there you see you got the rocket assembled. And it's starting to look like a rocket. So next is you assemble the payload bay. So you have to take those launch lugs out, because I put those launch lugs in just to glue, because if you go back, where's the slide? Here, it's composed of two pieces. There's an inner piece and an outer piece, and they come separate. So you have to glue these together. So what you basically do, you put the eye bolt in, you put some epoxy, and you slide it into the payload bay, and you slide it into the body tube, and you let it set. And that makes sure that there's no lip. It's going to fit into the tube seamlessly. So once that's done, you take it apart and you put them together, you screw them together and drill some more holes, and you put these threaded rods through. And those threaded rods are going to house something called the sled, which you're going to mount all your electronics to. See here, I've cut the threaded rod to be much smaller. And here you could see the inside of the payload bay. You could see this is the sled. And I 3D printed these mounts, which slide across the threaded rod. And this wooden sled sits there, and that allows me to mount my electronics. That's going to separate the rocket, or it's going to measure the flight performance. It's going to do all those things. And that gets fastened to that piece of wood there. Here, now I've drilled some more holes here, and those are just 2 bolts. And what happens, this is attached to the electronics inside of the payload bay, and that's attached to an E-match, which fires a charge that'll separate the rocket. And you can see the other side, it's got another 2 bolts to fire a charge at the lower part of the rocket. And you can start seeing some holes I drilled in here. Some of these holes are for air vents, and some of the holes are for these things here. They're called removable rivets. So when you put the rocket together, if you want a certain part not to separate, you put these rivets in place, and basically they just mushroom out. You put this part in, and then this part comes out, and it forces that part to flare, and it remains rigid, and the rocket can't separate. So the next step is to put my switch that's going to turn on and off the electronics. And so in this case, I use a switch, a push button switch that I'm going to put in one of the air vent holes, and I can activate it on and off. I don't need an external switch. I toggle on and off. Here it's a push button that goes, I push it in, and it's kind of like a push button. It's not a momentary. I can't remember what the other type of switch is, where you push it, it engages, you push it again, it comes out. So there it is mounted, and you can see the vent hole, the air vent hole, there it is there. And that switch gets epoxied. Here I'm using a clamp to epoxy it onto the sled. And there you could see the hole, you could see the vent hole, and you could see the little blue switch. And I use just I could use a toothpick, or I could use a pen, or I could use something, got a point, I push it, and that's how I turn my rocket on and off. And always you mark which way is up. You always mark it, because trust me, you will mess things up and put things in backwards, especially when you're assembling the rocket. So I'm down to, there's just a few more pictures. So here's the rocket painted. I've added these 2 things sticking out here. You can see them here, the launch lugs. And that's what goes on the rail. And that's what keeps the rocket going straight when it launches, to give it some help to keep it going straight. Once it reaches a specific velocity, the fins take over and it's able to fly itself. Here I've just got tape on it because I was painting it, and this is just primer, and you can see the fillets are a lot better. There's still a little bit of gnarliness there, but you know, that's easy to sand and fix that, and you get the rocket looking nice. And those spirals, this is a filler, it's a sandable primer. So you spray a couple coats of this primer on, you sand it, and those spirals disappear. So the final step, once you've got everything, you go and you weigh all your parts. You measure the distances, the length of the tubes. This now you're measuring the actual length of tubes. Back when I did the design in Roxim, I used what I thought would work, and what actually built might be, a little bit smaller, might be heavier. So it's important that you go and you weigh all of your components. and weigh your parachute, the shock cords, you weigh everything, the electronics. Then you go into open rocket and you override. Remember, it was showing, see here now, it's showing in grams. I don't know why that picture before was showing ounces and inches. But here it's showing, so I go in, I measure it, I measure the overall mass, and I override it. I say this is my specific mass of the rocket. I sum up all the pieces, and then I actually measure where I balance the rocket, and I measure where the center of gravity is, and I plug that in. So now I override what Open Rocket thinks it should be based on these parts. And this is going to give me a much more accurate simulation. So now I basically, next step is I go into motors and configuration here, and I select a motor. I set how long of a delay before the motor ejection charge goes off. Then I go into flight simulations, and I run a simulation similar to what you do in LT Spice. You would go in and set what the simulation type is, what voltage you've got, and so forth. And then you go in and you actually run the simulation. So here I've run 4 simulations, although they're numbered 4, 5, 7, and 8. And for different motor combinations, and that dash and the number is the delay for how long it's going to wait before the motor fires an ejection charge. And this is giving me the velocity off the rod. This is important because this is going to tell me whether the rocket's going to come off the rod and fall over, or it's going to go horizontal and go like a missile and potentially kill somebody. So the velocity off the rod, generally you want at least 14 meters per second, somewhere between 12 to 14 meters per second coming off of the rod. That's when it leaves the rod and it's actually flying, because at 14 meters per second, I know the fins are going to be working. So you can see these 2 simulations here. It's coming off pretty anemic. You won't want to use these motors. This is giving you the apogee, how high the rocket's going to go. It's going 300 feet. I would never fly a rocket with a large motor that's going 300 feet. No way. That basically the rocket's going to flop over. Another important aspect is the velocity at deployment. So when it reaches what's called apogee, that's the top of the curve, the rocket goes up, reaches apogee, slows down, then it comes back down. And so at the velocity at apogee is when you're going to open the rocket. Your electronics are going to come and it's going to open the rocket up. So you want the rocket to be going fairly slow. Now, if you've got the rocket going, like see here, it's going at 15 meters per second, it's still okay. Roxham is coming back and saying that's okay. For me, it's going a little bit too fast. I like it to be down, single digit meters per second, because I don't want the rocket to do what's called a zipper, where the shock cord comes out and it rips a hole or rips a side in the tube. And then it gives you the optimum delay, depending on the size of the rocket, the weight. This is how long the rocket's going to coast after engine cutoff, right? So after the engine stops burning, there's a delay that goes off. And here it's set to 10. And this is telling you it actually should be set to 3.8, should be set to 6, should be set to 8, 9, should be set to 8. Here it's set to 10. So this motor, we should reduce that down to about 8, just to reduce the speed. And so based on this now, I know what the parameters are to go and fly the rocket. The next thing is the max acceleration, and that's going to tell me what the biggest motor I could put in here. Normally, 10 Gs, 16 Gs, is fine, not a problem in one of these mid to high power rockets. But if you got something like 20, 30 Gs, you're going to rip the rocket apart. So that helps you to determine what size motor you're going to put. And that's it. So let me go back here and turn this off.
All right. Thank you very much. Interesting little overview there. even though I've seen some of your rocket exploits and what have you. I've never seen the little nitty gritty there. So let's start with the questions. We got two of them queued up already. So I believe Peter had your hand up first. Please come in.
Very interesting, Dave. Thanks for that. One thing, I've got a couple of questions, but I'll just do one for now. One thing I was curious about when you're building the fins and whatnot, when you're putting this together, how accurate do you need to be? For example, to go to if your fin is say 1 degree off, would that affect your flight greatly, or you need to be pretty much bang on?
No, it's got to be bang on, because even if it's a fin is misaligned by 1 degree, okay, what'll happen? The rocket will spin. The rocket will actually start spinning around. And some people want the rocket to spin because it's like a bullet. Sometimes, a bullet has no fins, but the way you get stability of a bullet going straight, you spiral it. So the bullet spins really fast, and that gives you stability. So the bullet goes straight, right? So, sometimes it's good, right, to have the rocket spin, but sometimes it's bad because you could get the rocket to be dynamically unstable. So there's something called a restoring force. So the fin makes the rocket, if the rocket gets perturbed, it kind of moves this way. The wind blows the fins and brings it back. Now imagine if it's blowing it back and it rotates around. So it blows it back and it goes this way and it rotates and it makes it go further, ends up being dynamically unstable, and the rocket just flops over and starts spinning, flying wild. So there's something called natural frequency. So to answer your question, Peter, it's got to be pretty accurate, because you don't want to induce spin unless it's something you specifically want in your rocket. You've designed it to have that spin.
Okay, thanks, Dave.
Hey, Al, you're next in line. Please go ahead.
Thanks. Thanks very much, Dave. That was really interesting. Just a quick question. I imagine the center of gravity is pretty critical. I'm wondering how you accommodate a changing center of gravity due to I guess you're getting a loss of mass in the engine as it burns up, and your center of gravity is changing.
Somebody's thinking. So that's why you have something called a stability margin. So what happens is, if you look at Barrowman's equations and most of the design, they take the body tube and they say you need to have the separation between the center of pressure, where the fins, the restoring force coming from the fins, the distance between the center of gravity and that restoring force, because that doesn't change, but your center of gravity will come down or go up depending on you're adding mass, or you're depleting mass from the motor. So that changes. So you want to have a minimum displacement here. So just in case you put a motor that's a little bit too heavier in, it comes down, you still got that margin, and you could still have that restoring force to make the rocket weather vane itself, right? So you have to accommodate that by having that stability margin. That becomes critical in something called rocket gliders, where they have an airplane and basically with a rocket motor, because in the case of a rocket, you want the center of lift to be behind the center of gravity. But in an airplane, you want the center of lift to be slightly ahead of it, because you want basically a slightly nose down attitude, because you want the airplane to always adopt a nose down attitude. You don't want the airplane to adopt a nose up attitude. That's really, really bad. So in a glider, that stability margin and the movement of that center of gravity becomes extremely critical, and you have to accommodate for that moving center of gravity.
Great. Thanks, Dave. I appreciate that.
Okay, Drew.
Yeah, that was really interesting, Dave. Did you get a new CNC?
Nope, that's the same one I was using to mill my PCBs. I got it from Peter's, the one that put the worm in my ear,
Yeah.
in my head, to go and mill PCBs, and I had it sitting here, and it could do so much more, and I just thought, okay, you know what? Instead of going out and buying parts, why not just go mill myself? So I just figured out how to use FreeCAD and how to get it to generate the G code to send it to the CNC machine to mill.
It was very nicely done. I was just wondering also the materials of construction for the tube. Is this all basically cardboard?
For that rocket I built, it's a little bit heavier cardboard. Normally, for like a really high power rocket, when you're flying a motor like K or L or M, you're going to be wanting to use a fiberglass tube or
Okay.
a carbon fiber tube, because at those speeds the rockets go in Mach. It's going Mach 1 or Mach 2, and any little restoring force puts a huge force in the tube, and the tube will just snap if it's not reinforced. But for that rocket, the motors I'm flying, it's not a problem. I just use cardboard.
It is commercial engines?
Yeah, these are just. I don't build my own. I can, and now it's now legal for you to build your own motors in Canada. But way back when, like 10 years ago or so, it was illegal for you to build your own motors. But now they've got a class called experimental motors, and so you go to a launch and you're allowed to launch experimental motors.
Just if I could interject here,
Yeah, go ahead. Sorry.
Is building your own the same as reloading, or is that different?
No, reloads. You could get commercial reloads. So it comes with a case. Now there's a single-use motor, which you fly and it burns once. That's it. You throw it out. That's a single-use motor. Okay. Or there's a disposable. That's also called a DMS, disposable motor system. There's single-use as well too. Same thing, but there's a reloadable.
Yep.
So it comes with a metal sleeve, and you put a reload in that sleeve, and the reload, you take it out, you throw it out, and the sleeve is still good. You put another reload in.
Okay, that's different from building your own, though. No.
Yeah, that's completely different from building your own.
Okay, sorry, Drew. Continue.
I don't mean that. One last question: where do you do this? When I looked into this as a kid, you could only do it on army bases, and you needed a firing area supervisor and all that stuff. Where in Canada or Ontario can you actually do this?
A model rocket up to a rocket of impulse G. Okay, you could launch anywhere you want.
Really?
You can go and launch this. You yourself can go and launch it anywhere you want, as long as the air reg says, as long as it's not a hazard to aviation.
So not at the airport then.
Yeah, so you won't be flying it near airport or near where there's planes that are going to be flying, and you're not going to be flying it into controlled airspace. That's a hazard to aviation. And also common sense, you're not going to be flying it in a populated area where it could come down and 10 peg into a house. So you got to use a little bit of common sense there, even though the air regs doesn't say where to fly it. They're just concerned of you flying things and hitting airplanes.
Okay,
But
thanks.
once you fly above G motor, all of a sudden Transport Canada gets involved, and you have to be licensed, you have to be certified, you have to launch it at a specific place that's authorized by Transport Canada to go and fly high power rockets.
Well, that's fair. That's understandable. Well, thanks.
Okay. I've seen a lot of horizontal rockets, but are there any I'd be more interested in being like Werner von Braun. I mean, like a V2, more of a horizontal flight. Does anybody get into that?
No, it's illegal. You're not supposed to. There's nothing in the air regs that says you can't launch a rocket horizontally.
Yep.
Right? It's friggin' dangerous. You shouldn't be doing it. You jeopardize people by launching something horizontal.
So there's nowhere where that's legal.
There's nowhere where that's to launch a rocket horizontally except like a rocket sled. But if you're flying something, like you could fly a rocket plane, which is going to go horizontally and go up, just like an airplane, but a rocket with fins, you're not going to fly it horizontally because you know what that's called?
A missile.
Anyone? A missile. That's called a missile. Right? So,
Okay. All right.
so I think the government and the military is going to have something to say about that.
Just with a name like Gunter, like it's in my blood. So what can I say? All right.
There are V2 replica, not V2, V1s.
Right.
There's V1s. I haven't seen a V2, but there are V1 replicas flying. At one flight, we were at a LDRS, Eric. You came down with me with your kids.
There was a
a
V1.
guy who had a scale V1 rocket there.
Oh, okay. Sehr good. All right. Okay.
And he wasn't German.
Okay, Peter, please come in. Oh, you're muted, Peter.
I think I have it figured out by now. Dave, a while back, you were talking. I don't know if you were just telling me about it or you did a presentation. I can't remember now. But anyway, what reminded me of this was when you were describing your air vents that you put in there. And I think you made a boo-boo with an air vent on a rocket. Can you just describe the? I think it'd be an interesting story.
That's right. Because what happened, it was the last LDRS launch I was at last year. I think it was last year. Took a rocket and I had my homemade. Someone's not muted. And so I made my own homemade electronics, put in a rocket. The rocket came off the pad and poof, it separated. The engine was still going and it just woo, 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 woo. It was great. People love that. They see when a rocket explodes and it goes all over the place. Everyone's like, woo, yes. It's like death and destruction, right? Yeah, but that was because it's one of two things. One, it was a very windy day and I had one air vent. And so I maybe, dynamic pressure of the wind going into the vent hole, causing the pressure inside the tube to go higher, which makes it thinks it's lower. Because as you go up, pressure decreases, and that's how you get your altitude. But if the pressure increases, it thinks it's going down. So if it's going up, it's detected launch, and all of a sudden the pressure starts increasing in that tube. It thinks, oh, we've reached apogee and we're coming down, open, right?
Mm.
Or it could have been just the mass of the air it's going up, and just the mass of the air coming down, it increased the pressure. I don't think it was that. I think it's more so dynamic pressure of the wind. That's why you need to have multiple vent holes to allow air to go through the payload bay.
Okay, Kevin, go ahead, please.
Okay, my audio working?
Yep, perfect.
Okay, good. All right. So I noticed you're weighing everything, Dave, and I see things like those metal eye hooks and complete pieces of plywood. Do you ever or maybe they need the strength? I don't know, but what about would you ever 3D print some of that stuff to save weight?
No, you wouldn't.
Drill holes in the plywood to
that
stuff, or doesn't matter?
That stuff I wouldn't 3D print that, because that's taking a lot of force when it opens, especially if it opens and it's going fast. Because remember I said that I have to get the delay in the motor such that it's slowing down. Because if it's going fast and it opens, right, what'll happen, it's still going through the air. That front part could catch the air, whip down, or the back part, it's got an opening, it could act like a little parachute, and it could really slow down, and the two pieces can really force against it, and you could rip. I've ripped shock cords right out of the motor mount in some flights where it completely rips right out of the motor mount.
Okay, so you're not like the backpackers, like even the plywood separated the circular discs, like even if you were just to drill holes out of them and stuff, or you're not like those backpackers that cut spoons in half to save a couple of grams.
Yeah, in this stuff, like yeah, there is a class of rocketry scale where guys do that, where they will lighten the rocket. You would because they want to lighten the rocket as much as possible. They don't want it heavy, and because they want to. If it's heavy, it takes much more impulse
Yeah.
to get it going off of the pad. If it's lighter, it goes faster, right?
Yep.
So potentially they get a higher altitude. So they'll do that in scale competitions. There's one guy I know, and he flies. He's like he he competes in the States, and they fly scale and very light rockets. So yeah, they do that for the stuff I do. It doesn't really matter because
Okay.
it's like a Windows system, a PC. It's got so much horsepower, you don't care. You just load up software and it runs, right?
Or get
So
a bigger motor.
yeah, you got so much power in that motor. Weight doesn't really matter
Okay.
unless you're trying to stick within a certain size motor.
Yeah. Okay.
Okay. Thanks, Kevin. Howard, please go ahead.
All right, can you hear me okay?
Yep.
Yeah. Hey, nice presentation, Dave. So do you think there's any value to having articulated fins to control the descent so when the parachute's deployed?
Yeah, there is something really cool. It's called backslider, and so as I think Al was asking about center of gravity, where placement of center of gravity. So what happens as the motor depletes? Okay, you could have it such that the rocket, as it's falling, it's going to fall backwards. So the fins have got more weight, so it kind of makes the rocket fall backwards, and it slides backwards, and the fins act like wings, and the rocket will fly backwards all the way down, and that's called a backslider. Very, very difficult to go do, but there are people that do that. These days, there are lots of guys. If you go on YouTube, there's lots of guys that are articulating the fins to keep it going straight. But more so, they gimbal the motor. They have gimbals, just like the rockets you see flying, SpaceX and Saturn rockets and whatever.
Thrust.
Whatever. They gimbal the motors, and so they gimbal them as it's going up. It's gimbaling it to keep it stable, right? So they do that, and there are people successfully doing that. There are people that's doing the fins, moving the fins, and you could do that. It's pretty dangerous, frankly, to be going and doing that, moving your fins around, because you want it static. But there are people. So absolutely, there are people that's doing that and doing clever things. You got to really know what you're doing, and then it involves a lot of electronics and a lot of software programming.
Yeah, that's interesting. Thrust vectoring. That would be cool to do that.
Yeah, and if you go, there's a guy, bpsspace.org, I think. If you go to his channel, he started playing around with vectored thrust, and those fins, the paddle fins that you see on the SpaceX, those paddle fins on the booster coming down. So he plays around with those, and he was able to successfully take a rocket up, let it fly up, bring it back down, and fire a motor just before it lands and make it land soft, completely vertical.
Pretty cool. Thanks.
Okay, I think that was the last of the hands that were up. Dave, do you have any telemetry on that, like recording on that rocket that you were showing off? Like
No, it hasn't flown. It's actually, the rocket turned out to be too heavy, and so I have to fly it as I was going to fly it. I was hoping to fly it in model rockets, but I over-engineer shit. I just overbuild, and the rocket's too heavy. Because in those simulations, you'll see, I was trying to see if I could get a G motor,
Right.
and it wouldn't fly in a G. I had to go to an H, which is high power, which means you can't fly it. You have to go to a high power launch.
Right, because that would. I think I saw an F motor in one of the pictures you had there.
Yeah,
That
yeah,
was
and
like a mid.
F is a model motor.
Right.
F and G's
Okay.
are model motors.
Would you have put any kind of telemetry recording in that?
Oh yeah, all my rockets.
All of them.
I've got telemetry. I just built one board now that I've been working on. It's flight tested. It works, and it's got a Wi-Fi downlink, and it's got Bluetooth as well. So from my phone, I can go and arm it. The electronics, I can say arm. Okay, you're on the pad. Go, ready for launch. And then it sends RF down to me. It sends Wi-Fi. It bleeps down. It sends periodically messages down telling me telemetry, how high, and it also records it to an SD card as well too.
Right. Nice. Okay. Very good. Well, thank you so much for that presentation. That was excellent, very detailed, and I think we all got exposed to something that we didn't know there before. So that's great. Okay, so moving on, we will slide into Charlie's discussion. He's going to be talking to us about an introduction to the Pico version of the Raspberry Pi ecosystem, I guess we'll call it. Both the original Pico and the been around for a year or so now, the Pico 2, which has, I think, the 2350 chip in it, and the variants thereof. So, yeah, please, you have the floor, Charlie.
Thank you. Just start sharing here. And let's see. Should be able to see that.
Looks good.
Okay, so this, the idea to talk about this a little bit came from some discussions we were having during our 4 days at Eric's Cottage. We got talking about, the differences between Raspberry Pis and Raspberry Pi Picos and Ws and so on, and comparing them to things like Arduinos for jobs. And so I thought it was worthwhile taking a couple of minutes to do just a kind of a 101 on this. So if you've already played with the Pico, this is going to be fairly boring stuff for you, I think. So to start off, a picture of a Raspberry Pi 02W and a Pico beside it, so you can kind of get a feel for the difference in size between the two. The Pico is quite a bit smaller, and has a much better sense of humor about things like voltages that you feed it with. It will run sort of 1.8 to 5.5 volts. But the big distinction is that the Pi 0 and the Pi 3 and 4 and 5 are true computers. They run a full operating system, and they're running a flavor of Linux effectively. You can essentially run all kinds of programs on them, understanding that they're not super powerful machines, but for a lot of the programming things we do, the Raspberry Pi series are great little computers. The Pico is not a computer; it's a microcontroller, so it's along the same lines as an Arduino or a PIC or something of that nature. But they are quite powerful, surprisingly. For the grand total of $5.65 Canadian as of last month, you get an awful lot of power. The Pico 1, the original Pico, is the one I'm mostly talking about here, has a 2040 microcontroller. It has a dual-core ARM Cortex processor with a flexible clock that runs up to 133 megahertz. Where Arduino's, I think, and Uno is running about 16 meg. So it has onboard 264K of SRAM, 2 meg of flash memory, and it has a USB port with it will do both host and device support. So you can treat the Pico as something that you're controlling from your computer, or the Pico can be the controller controlling, things like sound cards or well, whatever you can control with a USB. Programming it is pretty interesting in that you basically put it in a mass storage mode, and you just drag and drop your file on it, and then power cycle it, and it launches the program that you've just loaded in. It has some nice low power sleep and dormant modes, but generally speaking, it tends to consume more power than an Arduino, for instance. It has 26 multifunction GPIO pins, 2 SPI interfaces, 2 I2Cs, 2 UARTs, 3 12-bit analog to digital converters, and actually it has 4. But the 2040 has 4, but one of them is taken up for an onboard temperature sensor. It has 16 controllable pulse width modulating channels, so you can do motor speed control and things like that with it, or even some cool radio things that we'll talk about in a few minutes here. It also has an onboard real-time clock, which is kind of nice. Having said that, that clock does not have a battery backup. So if you power cycle it, it forgets what time it is, and you have to have it give it the time as part of its booting up procedure. I mentioned the temperature sensor. It has floating point libraries on chip as well, which is quite useful for doing any kind of math processing. We talked about FFTs at one point, and I think you could do a fairly simple FFT with this thing. And the other thing that's particularly cool about this is that it has 8 programmable I/O state machines for any kind of custom peripheral support. If you wanted to have 10 RS-232 interfaces, you could have those state machines set up as a RS-232 interface, all 8 of them, and then there's the 2 that are built in, and away you go. You'd have all of those interfaces, and a number of other things that you could do with it as well. The RP2040 Pi Pico wasn't out too long when along came the Pi Pico 2. It uses a 2350 dual core Cortex M33, and it can also optionally run RISC-V. Clock speed's a little faster, up to 150 meg instead of the 133. Got a bit more RAM, 520K instead of 264, and double the flash at 4 meg instead of 2. But it also has a bunch of security features built into it. So things like secure boot and trust zone. These are things that are quite useful if you're building Internet of Things devices and so on. But if you're like me, it's an extra layer of complexity. So if you don't need it, it's one of the reasons I've been sticking really with the Pico and haven't done much with the Pico 2. It consumes a bit more power, of course, because of that little faster processor, and it runs quite a bit faster. Oh, and the other thing is it actually has 12 state machines on the Pico 2 instead of the 8 that you get with the basic Pico. If anyone wants to interrupt, please feel free. I can't actually see the screen with presentation mode on this thing, so just shout over me.
Yep. So far, so good. Thanks.
Okay. So I like to call this thing a Swiss Army knife, the next generation. And it's really because of all of the interfaces that it can support. And those programmable state machines are a really powerful addition to a microcontroller. Rather than, with PICs, you buy the microcontroller that has the features you want. So if you need USB, that's one controller. Other one won't have USB, but it'll have RS-232, and so on and so forth. You can, with this guy, essentially fire up those state machines to produce pretty much any interface that you'd want to. The chip showing here in the middle is the 2040, and if you break into the 2040, as I had mentioned, it's got 2 cores, so you can run 2 completely independent threads, which is kind of nice, because there always seems to be something that you want to do on a regular basis, for instance. So you could, set one up as kind of doing the equivalent of a cron job while the other one collects and serves data or whatever. And it has 2 of these quad programmable input-output machines. Each of those, PIO 0, for instance, has quite a bit of logic in it. And we'll just zoom in on that a little deeper. It has instruction memory for those state machines. So you can have kind of 32 instructions to, shove a piece of data in here, add a number to it, and stick it out one of the GPIOs. Whatever comes back in that GPIO or a different one, pull it into the state machine, perform a bit more math on it, shove it into the FIFO register, which sets up an interrupt, and then the processor comes and reads it out of these FIFO registers. So there's I just talked about one of these, but this is the the brain of the state machine, if you like. So an example of how you would use that, if it's not obvious, let's say that you wanted to do a 7-segment display driver. So, if I want to display the number 1, well, I have to light up LED 1 and LED 5. So those will be 2 different output pins. And so the state machine would, if it has a number that comes in here, it would output, 1 and 5 in the IO multiplexing stuff. And, similarly for all of the other numbers. So you would have this 7-segment display driver basically is one of the state machines, and you connect the segments up to the pins. Of course, those are cheap and easy to buy, but why add another chip on your board if you can actually do it with the Pico that you're using for other things. They also come in wireless flavors. So the Pico W, instead of being sort of $545, goes up by $3 to $845. But it has an onboard 2.4 gig interfaces. So it will do wireless, and it will also do Bluetooth. Now they've released software for that. So it can be kind of a soft access point, supporting up to 4 clients, or it can serve data. And I'll talk about that in a minute or two. By the way, the wireless interface connects by SPI to the 2040. And yes, if you're looking at the Pico 2, there's a wireless version of it as well for also a $140 more this time. PC Mag did this comparison of which one was the winner when comparing these things, but I sort of thought that's a bit thin. So while I had shown that for someone else, I'll just bring up, I did a quick search on this just before the meeting started. And, you know, here's a comparison between the Uno and the Pico. You know, clock speeds 133 meg versus 16 meg, 264K of RAM versus 2K of RAM, 2 meg of flash instead of 32K of flash. The Pico runs MicroPython, but there's also an SDK for C and C++ for it, whereas the Arduino is pretty much only C and C++, which is cool if you love C and C++. You can use it with either controller, but I have trouble with C. Python seems to work with my brain a little better, so I was quite excited about MicroPython support for a microcontroller. And you know, the cost of the Pico typically around $4 whereas the Uno is running about $27 at least it was a couple of months ago. So what can you do with this stuff? Well, I've done a couple of projects with it, just playing with it a little bit. The Pico, not the W, just the Pico, just to learn how to program the thing. I did a temperature probe and a 2x16 character LCD display, just to make a thermometer. Just, you know, not a earth-shattering project by any means, but it's a good way to kind of learn how to run the thing. Then I've talked in the past about the APRS remote telemetry boards that I've been building for a ham club, and I replaced a bunch of the sensors on it with a Pico. So the A to D sensors for measuring voltages in the remote repeater location, temperature sensors, and so on and so forth. All of those things, watchdog timers, so that if the Pi goes off into space, it'll get a kick from the Pico. All of those things were implemented on a single Pico that I added to the board, and I took about $15 worth of components off the board. So and I think it became more reliable. So that was kind of exciting. For the Pico W, I did a couple of projects for it. One was just a clip-on LCD display that when the Pico comes up, it powers up and it uses DHCP to get an IP address from my network. But of course, if I want to talk to it or do anything with it, I need to know what the heck that address is. So I did a little bit of software that outputs the Pico's IP address. You can just kind of clip on an LCD display, and it will show what the address is. And then I did something like a remote light switch that was controlled over the net. Can do it with my phone or my computer, and eventually I plan on adding an Alexa interface to it. But basically, this is done with. I don't know how familiar you guys are with a REST interface, but created a very simple REST interface for this thing. So I built a remote weather station that serves its data as a simple web page. So when you take a browser and you navigate to that address, it pops up a very simple text-based web page that displays, data it's collected from the weather station. And then the other one that I thought was quite useful for me was a sump pump alarm that if the sump pump dies and the water level goes up, it sends me an email. It also sends me a daily email with its status and local temperature. So if the thing dies, I know it has died, and I can go and give it a kick before I have a flood issue to deal with. The Pico with these state machines can do some pretty interesting things related to amateur radio as well. So the flexible clock allows you to do things like um, uh, if you don't need the clock running fast, you can slow it down, save some power. The powering options, 1.8 to 5.5 volts is kind of important for some of our projects. In fact, the Pico or just a 2040 is what a lot of the Pico balloon guys are using. So you can hook it direct to solar panels and teeny tiny solar panels, and not have to add the weight of a battery to your Pico balloon flight. It's got these low power sleep and dormant modes. So if you only want to do, measurement every hour, it'll go to sleep, wake up after an hour, do the measurement, go back to sleep again. And those analog to digital controllers are quite useful for a lot of amateur radio things. I was poking around online, and I found someone had, this is from Instructables, someone has put together a SSB AM FM transmitter. Basically, this is the microphone with a little amplifier on it, but it could be a USB from a sound card. And what it's actually doing is it's using the pulse width modulators to essentially create the frequency of interest. And then it's using the pulse width modulators filtered so that they're more sinusoidal in shape to create the envelope. And they're using an analog switch, an external analog switch, basically. So it's summing in the two sides of the envelope on these two lines, and then clocking it, switching it on and off at the frequency of interest, and then a low pass filter after that, so it's not quite so dirty. And lo and behold, you're transmitting what the microphone put in place. A friend of mine has taken this a step or two further. He's actually got reasonable quality sound card equivalent coming out of this thing, and he's driving a transmitter with it to send APRS data. He's not interested in receiving APRS data. He just wants to get some telemetry information from a remote site that has no access. So he's using just a Pico with a 2040 and a small handful of external components. He doesn't even need this analog switch because he's actually using a 2-meter radio that he's just driving audio into. So he's using two of these pulse width modulators to kind of create the audio modulated on a tone effectively, like a it's a 1200 baud modem basically is what the what is sent into the radio for APRS. So there's lots of interesting things you can do with this little guy. And again, these are just some words around the what I just said in terms of the of how the thing works. And I believe that's almost the end. Need something smaller than that Pico. Adafruit has come up with a 2040 that it's a little more pricey, but it's about the size of a quarter. It still has the USB port on it. It still has all of the basic features, a few less IOs, but they do give you all 4 of the A to D converters, which instead of doing the onboard temperature thing. 13 GPIO pins. And well, I'll leave this for a second, and if anyone's interested, they can when watching the recording, you can pause it and read the details of it. Just the other side of it, this gives you another good feel for how big it is. This is, a USB-C connector, which is taking up darn near a third of the thing. So, and people are rolling their own with a 2040 chip. It's a pretty, the number of external components that you need is very small. So you can use the Pico board as the microcontroller, or just get the 2040 and roll your own, basically. And that is it. Questions and discussion.
All right, Dave, first out of the gate, please go ahead.
Yeah, Charlie, interesting. A very powerful piece of equipment there. That small little 2040 there with like the 16 pins or whatever, 10 pins or 12 pins. That I'm using the SP version of that in my Rocket altimeter. It's got Wi-Fi, Bluetooth, it's got everything. Those things are absolutely amazing. But that's the ESP version. I wanted to ask you about, but that's not what I wanted to. That's just a comment that those things are just so powerful. The amount of power those things have is just incredible. Multi-core, it's and it's. Do you know if it comes with a RTOS, or is it not running a RTOS at all?
No operating system at all on it.
Okay, because that's the one thing that the ESPs do. They have a RTOS, and so you're interfacing to that, and that allows you to do the multi-threading and multi-core programming.
Yeah,
anyway,
they're more the ESP32 is more equivalent to like a Pi Zero than this. This is truly a microcontroller. It's more like an Arduino.
Yeah. You had said that you for your home automation, controlling lights and stuff like that. You said you have a RESTful interface. Is that for Alexa, or is that for you to use yourself?
No, that's it's a standard interface for controlling things with a web browser. So you do it. You do things by navigation. So you know how when you go to a web page, you'll go to the address /directory / whatever, right? If you choose a directory, that will perform a function. Choose a different directory, it'll perform a different function. That's what the REST interface, how it works. So, so you navigate to light switch / on, and it will turn on. Light switch
So
/ off.
is it programmed in the back with Node.js or something like that? Are you using Node.js or something like? Because that's what most of those APIs use, right?
Yeah, and it's not that sophisticated.
Okay.
It's like I said, it's a very
Oh,
simple.
this is all hard coded in the microcontroller. Oh,
Right.
duh. Yeah. Oh, forget. I'm brain dead. Have you looked at all at Home Assist? It's I just stumbled across this the other day, as I think just post Eric's cottage. I stumbled across because I've been playing with VMs, and I saw
Right.
people loading this thing called Home Assist, and it's
Maybe Home Assistant.
yeah, no, it's Home Assistant. That's correct.
Yep.
Yeah, I'm
Yep.
just looking at it here. Home Assistant. Yeah,
Yep.
and it's pretty incredible because I think it it talks to all those sensors you've got, and you could all control it. You could set up automations, all kinds of stuff. It looks pretty powerful.
I'll have a look at it. It's a good tip. Thank you.
Okay. All right. Thanks, Dave. Peter, please come in.
Yeah, Charlie, thanks for that. It's I've never really paid much attention to the Raspberry Pis. I have a Raspberry Pi, the original, but I never even got around to doing anything with it. But although I'm told now I can't do anything with it. But what struck me the interest there is when you talked about rolling your own. And I think that's not a bad idea. It's certainly worth considering because I remember I acquired a bunch of Atmega 328P chips. They were that 32 pin, what was it, TQFP package, whatever it was. And I thought, well, you know what? I had a breakout board that would take that. So I thought I'll give it a shot. And I was able to solder on successfully. And anyway, rolled my own Arduino, so to speak. So I think anything's possible. So I think it's quite an interesting thing to give it a shot to try and roll our own. I know at $5 or $8 or whatever they are, it's pretty cheap, but still.
Yeah, well, particularly if you need a different form factor. So the Pico balloon guys, for instance, will roll their own on a thinner PCB and removing PCB material to get a couple more grams weight out of it.
Yeah.
And then you got guys like Dave Smith, who's he's got them being on his boards for his car. He's got his own stash of 2040s at JLC PCB.
Yeah, but he cheats. He gets them to populate the boards.
For $8 rather than trying to solder one of those puppies on.
Okay, thanks, Charlie.
Okay, Kevin, please come in.
Yeah, it was good, Charlie. It was. I have 3 sitting in a bag in a drawer here that have never been powered up. So it's good to see how much you can do with it. And I just went to that 101 Things website, and for Eric and Peter, so you can the guys got the same sort of complexity in a project where it does guitar effects amplifier, including equalizer, delay, reverb, chorus, flanging, phaser, tremolo, vibrato, all out of a Pi Pico. And
the link will be in the show notes, right?
What?
The link will be in the show notes, right?
Where do we put our show notes? I'll put a link to it in the
chat.
In the chat.
Sure.
Because I've looked at that and I go, oh, okay, well there's another project, not ham related, but
yep, still audio frequency.
I just took a quick look at the code. I mean, they're doing FFTs in this thing, and to do all the sound manipulation, it's like, holy cow. Anyway, pretty impressive. I mean, like how much
for $5.
Yeah. It's like it makes you wonder, right? It'll cost more to buy the jacks that you need to plug your guitar in and to go to the speaker than it will to buy the microprocessor.
Sad but true.
Anyway, thanks. That was good.
Okay. Yep. Charlie, you put up a page showing all of the projects that you have, I presume, completed with your Pico projects. What do you have uh, on the bench right now with regards to Pico? Have they gotten more complex?
No, it's a couple of these projects are off busily doing things, and right now I've kind of stopped looking at it because I've got some other shiny things that are taking some of my attention.
Okay. All right. Or anything planned, I guess, would be the follow-up question.
Yeah, no, I got Dave bit me at the cottage with his little mini PC, so
Right.
I've spent a week or two on that. In fact, that's what I'm using tonight, and so I'm learning how to do presentations with it. Linux is a little bit different than the Windows I'd been using.
Right. Oh, very good. Okay. Well, it's another tool in the toolbox, I guess, right? Now that
Absolutely.
you have chops. So that's good. Kevin, yeah, please.
I just, all this talk about Linux, and I finally swapped over this week as well. I'm running on Linux now as well. I'm just curious, show of hands, how many people here have Linux right now and are running it, or are going to be in the very near future?
Well, I'll
Three?
put my hand up.
Okay.
Yeah,
Four?
I see a few faces. It's hard to tell with the ones
Yeah,
where
the ones that are not. Oh, Drew's got, yes, Drew?
I think he put his hand up. Or
I put my
did you want to
that's
comment?
my way of putting my hand up.
Oh,
Yeah,
there.
yeah,
yeah,
yeah.
Drew putting his hand up.
That's what I thought you meant, you know?
Oh, okay. Yeah, no, that's a good idea. Yeah, I didn't even think of it.
Artificial hand.
Yeah, artificial hand. Yeah, no, I was being too literal. Sorry. Go
so,
ahead.
so it looks like about half of us.
Yeah, that's good.
Dave?
Yeah, Kevin, one of the things, remember we were talking about containers? So
Yeah.
I've been playing around with containers, and my God, like virtual machines are way the dinosaurs now. Everything should be run in a container. It's unbelievable how efficient and how small you can run
Yeah.
things in a container. Because my analogy is, just think, okay, suppose you want to run LT Spice. That's all you want to run. Okay, well, you got to install Windows. You got to buy a machine to run Windows. You need memory, you need CPU, you need disk, and you need all that to run Windows, just to run LT Spice. Now, in a container, you don't have to run Windows. It comes with everything, and it's just going to run LT Spice for you. That's it. Isn't that cool?
Yeah, I mean,
It's a fraction of the memory.
you're right. They're a lot more lightweight than VMs, but they're different security as well, right? I mean, there used to be a big issue with the Docker containers running with root access or something that they needed to have. And that was, I don't know if that's been resolved or not, or if it's still a thing. But
Yeah,
I have some containers that I run here too.
Most of the world, everything in like
on-
Amazon, everything you go to, almost every big website, Netflix, Amazon, Amazon.ca, you shopping, everything is containerized. It's all Docker, Kubernetes, everything.
It's all it's a lot more lightweight, and you can spin up containers as fast as you need them and all that. So, no, I know, and I do run some of them, but I don't know. Sometimes VMs are okay, sometimes containers are okay. It's like, I know what you mean though, and I have some as well.
Have you? Because I'm running containers in Proxmox. Are you running it in VMware? Can you run actual containers in VMware workstation? I don't think so. I don't think you can.
Trying to think if I've got a specific example. I know I run them on my base machine, obviously, but I think you can, because even servers.
Because everything I see, it's all everything about containers now. Because even Proxmox, you could take a native Docker container, bring it over, and it runs it.
Yeah, no, I think they have to be able to run in virtual machines, because all the server hypervisors are virtual machines, and the containers run on top of that, right? Because they don't provide an operating system.
No, it actually runs in Proxmox. It doesn't run on top of the hypervisor. It runs beside it. It's actually going directly to the
To the metal, really?
Yeah, because below you've got like your host OS, then you've got the hypervisor. Containers are actually bypassing that and actually talking to your host OS, and that's why it's so efficient, because you're not using that
Well,
hypervisor, right?
yeah, but the reason they're so lightweight is that there is no OS, right? There's just they
Right.
just package the stuff that you need.
Well,
So
no, they still
how does it?
need an OS, but they're
Right.
using the host
That's what I mean.
OS.
Yeah.
Yeah, whereas if you use a hypervisor, you have to load OS, then load the container, then load the VM on top of that, right? Or load the VM into that.
Well,
It's
yeah.
running an OS on top of the hypervisor, right?
Yeah.
Okay, may I suggest that you two get a room?
Sorry. Yeah. Not that has nothing to do with ham radio.
We need a rabbit hole counter here, I think. All right.
Well, that was only one.
That's right. Well, yeah, in the last 5 minutes, maybe. Anyway, very good. Oh, interesting. Yeah, all these topics that you can just keep going on and on with, right? So, okay. Well, thank you again for your presentation there, Charlie. That was very informative and opened eyes, I think, to even those that were somewhat familiar with the Pico ecosystem. So, seeing as it's already somewhat after 9, 5 after 9, I think we may forego the traditional round table talk. But what I will do in its place is ask if there's anybody that was planning on talking about something that they'd like to share with the group. Please put up your hand and we'll just zero in on those, if any. That wanted to share what their current workbench holds or projects that they are, about to work on or, want some help on. Anybody come in now? And if not, then I think we will perhaps call it an evening. All right. Well, we have a December 17th meeting on the schedule that is still on the official roster. So I presume that's going on, even though it is a week before Christmas week, whatever we want to call it, I guess, Christmas Eve. So if everybody's good with that, we will proceed. I guess a week prior is still reasonable. So Peter? Yeah.
I was just going to say, do we want to have the meeting on the 17th?
In the past, we have forgone the regular meeting, but it just depends on whether we can get a sufficient number of people. Anybody have a problem attending that meeting?
I should be around.
That's here.
All right, sounds good then. Okay.
All right. Yeah, I think we'll go ahead with it then. So we'll announce it prior to, as per usual, and I guess that's a wrap. So thank you very much for your participation, everybody, in tonight's meeting. And
very interesting tonight.
Yeah, absolutely. Expanding the horizons, right?
Guys. Way too many horizons.
Yeah.
Thanks, guys.
Okay.
73 all.
7-3 all.
Bye, guys.
Thanks.